All right, this is part 2 of the Laplace transforms differential equations lecture. At the end of last time, we had solved this differential equation here by Laplacing both sides. We put in the number 12 here and 25 here, and we're putting in a step input of 25 here. So we Laplace both sides. We went through solving for x of s with the step input of 25, so we ended up with this transfer function. Sorry, not transfer function, just Laplace transform. We needed to invert it, so we did partial fraction expansion based on these roots here, and ended up with, at the end of the day, we ended up with this solution here. And we talked about, oh, that was horrible. We talked about how the roots ended up here and here in the exponentials, and they were both negative, so these terms damped out as time became large. The roots are real, so we just get exponentials here. We talked about how if we had one of those roots or eigenvalues that was positive here, then it would blow up. And then the next thing we were going to talk about is what if the roots turn out to be complex, because you can take the roots of a second order polynomial and you end up here. So I'm going to reduce the damping from 12 to 6. So that changes the number here. So when you Laplace, you get a different polynomial in the denominator. And so if we find the roots of that using MATLAB, your calculator, or the quadratic formula, we get a set of complex conjugate roots minus 3 plus or minus 4i. So then the expansion is in terms of those roots rather than the previous real roots. Take the inverse Laplace and you get terms that look like this. So now we've got a real part and an imaginary part of the root that shows up in these exponential terms. So what's next? Well, we have an e to the minus 3t that we can factor out. And that leaves these terms in here. And so what does e to the I times something mean? Well, the math guys tell us that this is exactly what that means. And you can actually prove this by doing the Taylor series expansion of this and each of these terms, and it turns out they equal each other. So e to the I something is cosine of that something plus I sine of that something. So if we substitute that formula in for each of these terms up here, goes down here, we get sines and cosines. So what that means is that when we look at this solution, we get a steady state part that's the same as we had before, and now we have a transient part that is damped because the real part of those roots is negative, so the minus 3 causes this to go to 0 as time gets large. But as it does that, it oscillates, as sines and cosines tend to do. This is the angle theta of the cosine, and so 4 is the frequency. Radians per second times seconds gives radians, are the angle. So this 4 is the frequency of oscillation. If you want to, I've done a little side note here. If you plot sine theta, it goes from 0 to 2 pi as it oscillates. So if the angle is 2 pi, it's gone through one period. So that means that 4 times t, which is the angle in the cosine up here, has to equal 2 pi at that time after it's gone all the way through one period. So you can calculate the period as 2 pi over the frequency, or the frequency in hertz, really should call this f, is 1 over the period, because this is cycles per second, this is seconds per cycle, and that's omega over 2 pi. All right, so if we get real roots that are negative, it damps out. If we get imaginary or complex roots where the real part is negative, it damps out, but it oscillates. So we can define the nature of the response or dynamic stability by looking at the real parts of the roots of the characteristic polynomial. If they all have negative real parts, then we have the first case we looked at, which means it damps out to the new steady state value, it's non-oscillatory, and it's damped. And if you plot the roots, they show up over here on the left side of the complex plane, imaginary real axis. So you see these over here, they're both real, they're on the real axis. They're negative, so we get the damping and no oscillation. All right, if we have negative real parts and some imaginary parts, then we get the second case we looked at. It's stable, it's damped, but it oscillates because those sine and cosine terms come from the imaginary part. Plot the roots on the complex plane and you can see they're still on the left side, but now there's imaginary parts up and down. Case 3, what if we have one or more zero real parts? That means that you have e to the 0t and it does not damp out. So that's called marginally stable because it's on the borderline between stable and unstable. And if you have some imaginary parts, you get some oscillation. So what it does is it goes up and then it just keeps oscillating forever. It does not damp out. One of those terms does not damp. And then here's that other case we looked at. What if we have a positive real part? All it takes is 1, and we get an e. That's not an e. Here we go. An e to the positive number times t, and that's going to blow up. So that's called unstable divergent response. It can be oscillatory or non-oscillatory. All right, so we've really started doing what's called a root locus plot, which is how do the roots vary as a parameter in the system changes. And so we're going to look at just b, because we've already done b equal 12, and we've done b equal to 6, and we've seen that the response of the system changes depending upon what the value of b is. So we can plot the roots of the characteristic polynomial, which end up being in the solution here and here, and then we can see, without actually going through the inverse Laplace transform, we can see what the solution is going to be like based on just what the roots are. So here's the two we've already done. We did b equals 12, and we got 2 real negative roots. We did b equals 6, and we got complex conjugate roots still with a negative real part, which means it's stable. And so we can do a bunch more. Here's those 2 that we've already done. This is 12. This is 6. So let's add a bunch more. This is done in Excel. Here's the value of b in this column here. And here's the roots, the 2 roots that we get over here, real and imaginary parts. And here's the root locus plot. This is b equal to 12 here and here. And then as b decreases, the roots move, if you consider b a parameter. And then at this point, the roots become complex as you continue to decrease b. So b equal to 6 is a case somewhere along here where we got imaginary parts as well. And so you can look at this and say, okay, the value of b affects the response of the system, and as you get b less and less, it becomes more and more oscillatory, and in fact this is approaching being unstable. And this is the value when b is 0, we're marginally stable at these 2 points here. So this is a nice design tool because you can see how b affects the response of your system. All right, the last part of this is some kind of miscellaneous notes about inverse Laplace. If you have repeated roots, which means you have 2 roots that are the same, really that means you have like s plus 5 squared. When you do an expansion, you can't just do s plus 5. You have to include s plus 5 and the squared term. Just the way it works. So whatever order polynomial, order of factor here, you have to include that plus all of the lesser values. Probably remember this from differential equations. That's note number 1. Note number 2 is if you have complex roots, often it's easier to leave the complex roots together as a second order polynomial like this, rather than splitting it up like I did earlier into the 2 complex parts. That's because the algebra gets kind of messy if you include all of the i's, the imaginary parts. So you leave it like this, you expand it in terms of the real root, and then if you have complex conjugate pair roots, you expand it like this, rather than doing the individual terms like this. It just makes the algebra easier. And this is the other way that you probably learned in differential equations to find those parameters, is you simply multiply both sides by the common denominator underneath. So that's the thing up here. Multiply both sides, that knocks out the s and this here, and you get this form here. Collect terms, and then what you do is you equate equal powers of s. So this is a constant, this is s to the first power, this is s to the second power, and so this is going to be equal to 25 because there's no s's, and then this is going to be equal to 0 because there's one s, and this is going to be equal to 0 because there's two s's. So those are the three equations that you need to solve for the three unknowns, and this one gives us k is 1, and then you can substitute that into the two equations here to get the other values for a and b. So you get this, the real root term, and then you get the second order term that comes from the complex roots. Now what do you do with this? Well, you look it up in the tables. I'm going to flip down to the entry in the table that matches this thing. It's actually in this form. It's got s squared plus something times s plus something, and then on the top we've got s plus something, alpha. So you go down to the table, and you see that that matches this. And the way you match it is you say, okay, it's got a second order polynomial here, and it's got the s plus alpha here. And then here's what your inverse Laplace is right here. So you just figure out what alpha is and what zeta and omega is, and then you stick it in here and you're done. Nice, right? Takes a little bit of time. The first thing you match up is you say, okay, the 25 here has to be the omega n squared. And then the 6 here has to be 2 zeta omega n. The s squared is good. And then this has to be alpha. So that's what I'm doing here. Omega n squared is 25. 2 zeta omega n is 6. And so that gives me these that I need to stick into my formula. The only other thing we need to here's alpha is 6, is that the formula needs a 25 here. It needs an omega n squared, and we don't have that. So what we do is we multiply and divide by 25, and then we use the table just on this part and make sure that we multiply by 1 over 25 when it's all said and done. So here's the multiplier, here's the formula that we got from the Laplace table I showed you down below, and you work all the numbers out, and here's the solution that you get. Again, so this is the easy way to do it, is to use the Laplace tables. By the way, this table and the other side of it is posted on Blackboard along with a lot of examples of stuff that I just did. Alright, so that's the end of that lecture, and you're now prepared to do the homework that's posted